Now, one question that I would hope comes up right away is how the heck does that work? All I do is I take the matrix A and I keep multiplying it. I take the norm of the result, I multiply it again. I just keep multiplying A over and over and over and over and over. How's that working? How does that give me the largest eigenvalue and eigenvector? So let's take a look then at this random vector V. The initial one we took a guess with, right? We're going to go ahead and decompose this. Now, let's not get the subscripts and superscripts confused here. V0 is the subscript, or sorry, the superscript for the guess. But we know that any vector can be decomposed into a linear combination of the underlying basis. In our case, we have an eigenbasis for this matrix. So we're going to go ahead and say, all right, this is a sum of B0 times V sub 0. Remember, and I'll put a little parentheses here so you don't get confused, plus a little bit of a component of the second eigenvalue plus onwards until we get some component of the final eigenvalue and eigenvector. So these V's are eigenvectors that form the eigenbasis of this matrix. But we can just take any combination, we'll end up with a random vector V0. Now, let's go iteration by iteration, see what happens. I'm going to take A, multiply by this V sub 0, and I'm going to get B0A V0 plus B1A V1 onwards, BMA VM. I could have started counting at 1. Maybe I should have because the M dimensional, but you get the picture, it applies. And let's just keep going. I think I'm just in my Python head. I always count at 0. Okay, we have this expression. That's the first step of the algorithm. Let's pretend we do the normalization for you to see this, why it works. I don't really want to go through that level of math, but you'll see what happens next. So our big key here to use, though, is remember, by definition, this A V0 is equal to lambda 0 V0, simply from the eigenvalue definition. A V1 is going to be equal to lambda 1 V1. Lambda 0 is the eigenvalue there, and lambda 1 onwards, and this one, of course, will be lambda M Vm. So now let's go to the next iteration and see what happens. Let's say I'm now doing this, the second time. And let's go ahead and say, let's put a 1 there. Now I have this B0 we're never going to touch it, but I'm going to take A times lambda 0 V0 plus B1, and I have A now multiplying lambda 1 V1 plus, it goes all the way down. We're running out of space there. You may be seeing what's happening. I'm going to pull out this lambda 0 here, and I'm going to use the fact that A V0 is equal to lambda 0 V0. So now I have this is equal to B0 lambda 0 squared times V0 plus B1 lambda 1 squared V1. And it happens again down here, lambda M squared Vm. Let's go to A Vk. I've done this k times. Let's say k is a lot, enough to see what's important and not important. I'm going to have B0 lambda 0 to the k, and let's put a minus 1 to be consistent. And I'm now going to have lambda 1 to the k V1, and then I have everything down here, lambda m to the k Vm. And here's the part where we really see what happens. Now, looking at this, if k is a pretty big number, lambda 0, because it is the maximum eigenvalue, will be much larger than lambda 1 to the k. Let's just make it real simple. Let's go ahead and factor out lambda 0 to the k. And that gives us B0 V0 plus B1 lambda 1 over lambda 0 to the k V1 plus, we're going to have lambda m divided by lambda 0 to the k Vm. Dun, 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 dun. That's the magic result. You see that a v to the k minus 1, k is getting bigger and bigger. Lambda 0, when I pull it out here, you're going to get these terms to die. Because if lambda 0 is greater than lambda 1, this entire thing raised to the k will eventually go down to 0. Same thing down here. Now, it depends on the convergence. We'll say that this technique has linear convergence. It's order of lambda 1 over lambda 0. So it really depends on how much bigger the largest eigenvalue is compared to the second largest eigenvalue. And that's how fast you're going to find your maximum eigenvalue. When does this fail? It will only fail if in our initial random vector, it was parallel to the largest eigenvalue. So fails if random guess v0 is parallel to v sub 0. That's a really terrible way to write the subscript, I know, I'm so sorry, but it will fail if we don't have any component. If this component, if b0 here was 0 and we didn't have a component from the largest eigenvector, we would never be able to get that information back. So that's the only time this can fail. In my uses, it's never failed, but that's just the mathematics of it. This is such a simple, such a cool algorithm, and I really hope you enjoy it as much as I do. Good luck.